Great, thanks Aaron, and thanks everyone for still being here at the end of the day on I think it's Friday today, especially to those who've come a long way to be here. So this is joint work with Pavlo Blavatskyy from Montpellier Business School. And as Aaron said, we're interested in estimating attitudes towards risk and ambiguity. So just to make sure we're on the same page, let's quickly establish what we mean by risk and ambiguity. So I'll illustrate that with two acts. So think about $100 being paid out if a red ball is drawn from an urn, standard urn drawing exercise. So act F, think of that as the can I point here? Yeah, I can point here as well. As the urn on the left. This contains 50 red balls, 50 blue balls. So we know the probability distribution of outcomes associated with this act. We've got a 50% chance of winning. This is a risky act. The act on the right, we know there are 100 balls in there. They're red and blue balls, but we don't know the composition. So we don't know the exact ratio. So this is an ambiguous act. So an individual is risk averse if they prefer an even bet to the risky act, and they're ambiguity averse if they prefer the risky act to the ambiguous act. So those are the things we're going to be talking about today. Now, why do we care about ambiguity? I want to argue too that ambiguity is pretty commonplace. So most of the decisions we make in life involve some uncertainty about the actual probability distribution of outcomes. So think about choosing a career, choosing a life partner, an investment strategy. These are all very important decisions, and we're not completely familiar with the probability distribution of outcomes over these decisions. And also the mundane. So think about deciding what to wear each day, engaging in conversation. There's some ambiguity about what might arise from those decisions, and we don't really know the distributions associated with those. Now, it's relatively rare, having said that, to actually be able to study attitudes towards ambiguity. So it's difficult sometimes to separate attitudes towards ambiguity from the inherent ambiguity involved in the situation. So in a lot of situations that we might want to study, we don't actually observe how much ambiguity there is. We might just observe the decisions of an individual, and to separate out actually how averse or seeking towards ambiguity an individual is, we can't really do that until we actually can quantify in some sense how much ambiguity they face. Now, we could do that in an experimental environment, but budgets are typically limited. So our goal here is to estimate attitudes towards risk and ambiguity in a setting, quasi-experimental setting, with large stakes. And we're going to test between or compare different models of ambiguity attitudes, and also along the way illustrate how we might go about eliciting attitudes towards ambiguity in strategic environments. So that's our goal for the rest of today. Our laboratory is the Swiss implementation of the television game show Deal or No Deal. Is there anyone in the audience who's never heard of Deal or No Deal, or never seen any of it? Okay, there's a few of you. Great. So we're going to play a little game during the talk today, which is great to keep everyone awake. So I'll show you an episode, not literally an episode, but my characterization of an episode to illustrate what how the game show works. So there's something special about the Swiss version. Most versions have a sequence of decision problems, which are essentially dynamic lotteries. In addition, in the Swiss version, there is a game that takes place before the individual sequence of decision making under risk. So we use the game to elicit attitudes towards ambiguity, and then we have a sequence of decision makings by an individual, and we can use that to learn something about risk attitudes. And contestants can win up to $250,000 Swiss francs, which is that's a lot of money. And this was our sample is about 15 years ago, so it's even more money. So we've got data from 267 episodes from this show, comprising 1,335 contestants and a range of decisions in both the strategic game and the non-strategic game. Great. So we're going to take two approaches. So the context I want to lead you through is that imagine you're playing this game, and at the start of the game, there are 5 players who don't know each other. They don't know each other's preferences. So they don't really know how they're... So this is a situation of ambiguity, perhaps. So we've got 5 players playing this game, and they don't know the preferences of their rivals. They've never met them before. So how would you form beliefs about the strategies of your rivals? It's not quite clear. So there's also, in this strategic segment of the game, there's no opportunity for these players to talk to each other. So I can't use cheap talk to try and coordinate or influence the decision-making of my competitors. All I can key off is, in some sense, if I'm a student of this game show, if I've seen it before, and many of the people who go on the show have seen the show before, I might know something about the way that people have played this in the past. So I might have some idea about, the probability distribution of decision-making of people who've played this game before. So there's some kind of context that I would have gotten for that, but I don't know the particular strategies being used by my rivals. Great, thank you. That was great timing. So we take two approaches. So one I won't talk about really at all today. One, we look for an equilibrium among representative agents who are risk and ambiguity free. And it actually does relatively well. It explains, or is consistent with the decision-making of about 85% of the contestants. Now, a feature of, as soon as we posit an equilibrium, we presume a mutual understanding of equilibrium strategies. And given this context, I think that's a strong presumption. So we want to take an additional method into the data to try and allow for, relax that idea that we have a mutual understanding of equilibrium strategies, and in fact, admit the possibility of ambiguity. So if we impose equilibrium, this admits no role for ambiguity, and we have no way to learn about attitudes towards ambiguity from the data. So our second method, yeah, Ariel. Sorry, say again. So I guess if I'm ambiguity neutral, I'm treating any ambiguous act as if it's a risky act in which I've got the correct probability distribution, even if I don't know that. So in some sense, I'm just ignoring the ambiguity in the situation and just treating it as a situation of risk. How do I do that? Yeah, that's a good question. That's a good question. So I need to know, in order to get this started, I need to know something about the probability distribution of probability distributions at another level. Yeah. So imagine you have some kind of prior over probability distributions, then you're going to behave. Yeah, okay. Oops, going all the way back. So our approach then is going to be to treat the contestant's problem as a dynamic optimization problem under ambiguity. So we'll solve each contestant's dynamic problem within a maximum likelihood routine. And where's the ambiguity coming from? It's because I don't know the strategies of my rivals. So we're going to take the empirical distribution of rival strategies from the game and use that to say something about the distribution of strategies that players might anticipate, and this is going to be the source of the strategic ambiguity. Great. Now, in terms of identification, there's quite a bit of variation in the data. So to identify risk attitudes, we need variation in the attractiveness of risky offers. And to identify ambiguity attitudes, we need variation in some sense in the sensitivity of the ambiguity acts to probability assessments. And I can show you a picture a bit later to give you a sense for what that variation might be. Okay. So I'm going to skip over in the interest of time ambiguity, I mean, the literature, but I want to highlight at the top the idea of treating a situation like this with treating a game as a situation of strategic ambiguity is not new. It has a long history dating back at least to Luce and Raffa, but there's a nice paper by Aumann and Dries which goes into it explains this, I think, quite carefully, and so we draw on that a little bit, our inspiration for our approach. Okay, so we examine 5 models of ambiguity attitudes, relatively selective in terms of these are the models that we could imagine that we could solve using the data that we have. So the first is the simplest, that an individual treats an ambiguous situation as a risky one. So what are their preferences? So an individual faces an act F. So an act maps states onto outcomes, and they treat their situation as if they have the probability measure P. And so then I just take standard expected utility calculation with respect to that act F using that probability measure P. So therefore I treat the ambiguous act on the left as if it's a risky act like the one on the right, where we might shift around that red bar according to how optimistic or pessimistic I am in some sense. Next, we look at max-min expected utility. So think of this as being, I can imagine my prior in some sense is that there are 3 possible kinds of strategies that my rivals might adopt, and those give rise to different probabilities of me winning this game. So I might be really pessimistic, the one on the left. I might be moderately, have an even-handed idea, the one in the middle, or I might be very optimistic, that's the one on the right. A max-min expected utility optimizer will gravitate towards the most pessimistic assessments. They behave as if they're an expected utility maximizer with respect to the most pessimistic of the possible probability distributions that they could take to their situation. An alpha max-min expected utility maximizer is going to take the most pessimistic and most optimistic and use both of those and have some kind of weighted average of those two. So the alpha parameter describes in some sense how pessimistic I am. The higher is alpha, the more weighting I give towards the most pessimistic of those probability assessments. We also look at a relative entropy measure. So this is really closely related to the max-min model. So in addition to choosing the probability measure on the basis of the most pessimistic possible outcome, I'm also thinking about how close it is to some reference probability measure. So there's some reference probability measure Q, and I've got some kind of distance measure for how far away this probability measure P is, and I take that into account when I choose this, choose the probability assessment. So it's somewhere between the most pessimistic and something that's the most common or focal or the modal probability distribution. And finally, we look at the recursive expected utility model, also known as the smooth model. So in this model, in some sense, we repeat the expected utility calculation and we wrap that on top. So in addition to integrating over the distribution of possible outcomes for a given probability measure, we then integrate over the probability distributions that we could rationalize, given the data that we see. So I have 2 levels of smoothing, one over possible outcomes given a probability measure, and the second is over the probability measures that I can rationalize themselves. So I think that's why we call it the smooth model. It's also kind of recursive in the sense that we recursively apply utility transformation and this second curvature transformation. So if phi is concave, then we have ambiguity aversion. If it's convex, then we have ambiguity seeking. Just like the counterparts for risk attitudes. Okay, so let's play our game. So a contestant playing this game, there'll be 26 people who turn up. 5 of those will be selected on the basis of some general knowledge quiz or basically trivia quiz. Of those 5 contestants, bless you, one of those will be chosen. And this is the strategic game that we'll talk about in a moment. And then that player that's chosen plays this sequence of decision problems, which are basically dynamic lotteries, where they have an opportunity to exit for monetary reward at each stage. So let's work backwards. We'll talk about the non-strategic game first. So in the game, there are 26 possible dollar amount or Swiss franc amounts that a contestant might have in their briefcase, which is hidden to everybody. So I'm endowed with a briefcase. I don't know what's in it. I just know it's one of these 26 amounts, which are each equally likely. And what happens is I get to open the other cases. So each time I open another case, I reveal something about the distribution of what's in my own case. So in the first round of this game, I'm going to open 6 cases. So here's what happened to one of the contestants. And then I get a take it or leave it offer. So I get a bank offer, and they're usually unattractive at the beginning to build, so players don't leave straight away, and then they get more tempting as the game goes on to build tension and entertainment value, and to aid the identification of our estimation routine. So bank offer of $1,300. Contestants ask deal or no deal. So they say no deal. Second round, they open 5 cases. Just like that. There's a bit more tension. It's a bit slower. They're doing one by one in the game. And then they get a new bank offer. If I say no deal, I keep playing. I open 4 more cases. I get a new bank offer. If I say no deal, I open 3 more cases. I get a new bank offer. And it starts to look a bit better. So at this point, it starts to get a little bit tempting. So 17,000 Swiss francs is a reasonable amount of money, even for someone with a Swiss income. But there's some vulnerability here. So these 2 big amounts here, the next round, the contestant's going to open 2 cases. So they might think, well, there's some chance I could knock both of those out, and my value is just going to collapse. So they say no deal, move 2 cases, and they, in this particular game, they knock those 2 out. So then they get a new bank offer that's much lower. They say no deal, remove another case, new bank offer, no deal, remove another case, no deal, remove another case. And their bank offer starts to improve now, look a bit more attractive again. And at this point, this contestant actually said yes. So they took home 9,000 Swiss francs. And it turns out to continue the entertainment, they also explore what might have happened had they played on. So they can remove 1 more case, and they would have got a bank offer that's quite generous, 15,000. So that's the non-strategic game. So in this game, we can say something about attitudes towards risk. And we need to have Bellman equations for this conference. So, so let me quickly go. So a player in this game, thinking about a player in a particular round R who has a set of briefcases S, set of possible cases, monetary amounts that could be in their case S, and they face a bank offer now O with preferences or risk attitudes theta. Their problem is defined as follows. So they can either take the bank offer for sure, or they get a continuation value. And this continuation value is recursively calculated. And the nice thing about this problem relative to a lot of the applications we've had in the conferences, it's a finite horizon problem. So we can just use simple backward induction. We don't have to worry about a fixed point for this dynamic problem. So we just start in the last round where it's just a simple lottery, and then we can work backwards. The way I've set this up, everything is in terms of certainty equivalence. So we've undone all the mappings, and it turns out that's important for comparison across different models, because some of the models have different mappings involved. So especially when we come towards the strategic game, that becomes more important. So we can calculate the continuation value at each possible stage of the game. It's also important for us to value the expected value of this whole game in order to think forward when a contestant is playing the strategic game. They have to have an idea about what is the continuation value when they actually play the game by themselves, should they win the strategic game. So we need to have an initialization of the expected value of that whole game as well. Great. So one of the features of this is I need to predict the bank offers that might come. And it turns out they're very predictable. So we assume that contestants can predict those. And here is our evidence that they're predictable. So here's a really simple model. So a log linear regression with a bank offer and the expected value of the remaining cases that could be in the contestant's case. And if we condition this by round of play, our R-squareds are pretty close to 1. So this explains almost all of the variation, with the variation being particularly good in the later rounds where the decisions are more difficult. In the earlier rounds, the performance is not quite as good, but the bank offers are so terrible that nobody ever accepts in those rounds. So it's not so important. So we treat that as being known. Okay, so the strategic game. So the strategic game is where the ambiguity attitudes are coming from. So let's have a quick chat about that. We've got the same set of 26 briefcases, but there's different information in them. So now we just have numbers from 1 to 26. And what's going to happen is it's like a game of blackjack, or I think. So I'm not a card player, but something like that. So each contestant gets 2 of these cases, and the winner is going to be the one with the highest aggregate. Now, what happens, first of all, there's 2 rounds of play. In the first round, I privately learn my first case. So let's take the perspective of contestant 1. They learn they have the case 20, they have 22 in their one of their cases. And they also learn that their rivals don't have 22 in any of their cases. So that's what they learn in the first round. And now I get a bank offer, and it's always 2,500 francs, Swiss francs, in the first round of play here. So I get to say, okay, do I want to take that bank offer and leave, or continue to play on? Now, if I exit, and as you see here, contestant 3, who got a low first number, they exited the game. When they exit, they reveal both of their cases. So the other players also learn this information, so they learn what's not inside the remaining cases. Second round, I learn my second case, and then I get a new bank offer, and that's always 1,500 Swiss francs. So then the contestants make a decision. 3, 4, and 5 exit at this point. So then there's just 1 and 2 remaining, and the higher aggregate wins. So contestant 1 was the winner of this game. Okay, so what do I get? I get to keep playing. So if I win, I get to play that non-strategic game where I could win up to 250,000 Swiss francs. So the game that we went through a moment ago, that's starting that game is the prize for winning this first game. Yeah. So we need to, that's why we need to value that non-strategic game. So how are we going to solve this game? So the probability of winning the game, my perspective at each stage is, it depends on the information that's revealed so far. So what I've seen inside my own case, and also the cases of any exiting players so far. And also it depends on my conjectures about my rival strategies. So this is where the ambiguity comes in if I don't know their strategies. So the premise that we have is that players understand the game and they can calculate probabilities. And it turns out it does take a while for the computer to calculate these probabilities. So a few days, given the dimensionality of this problem. So it's as if consumers understand these probabilities, but they don't know the strategies of the rivals, and that's the source of strategic ambiguity. So we're going to assume that players take cutoff strategies, and then we're going to look for the empirical distribution of cutoff strategies from the data and use this to define the set of possible probability measures over the probability that you're actually going to win the game. The integration of this distribution, the way we do that is this is contingent of our model of ambiguity. So we're going to do this separately for each of our 5 different models of ambiguity attitudes. Cutoff strategies, we're going to define those by gamma. I think that's pretty standard. The act of winning the game, I can win the game either if my rivals exit, so this is where the strategies come in, or if I have a set of cases that dominates them in the sense that it has the higher aggregate. So here's the dynamic problem I face now in this strategic game. Sorry? Yeah, so in the first stage, the only information I have is my own first case, so I condition only on that. But in the second stage, I'm going to condition on both of my cases, plus the exit decisions of my rivals and the cases that they've revealed at that point. And that's public. So if I exit, everybody sees that. Yeah. Okay. So in the second stage of this dynamic game, we're thinking, okay, this is the terminal point. If all this pans out well, I'm going to play this non-strategic game by myself. So I'm thinking, okay, if I accept the bank offer, I can take that and go away, or I get this continuation value. And how does that defined? Well, it depends on our model of ambiguity attitude. So let's take, first of all, the perspective of a subjective expected utility maximizer who ignores the ambiguity in the situation. So what do? Well, they're thinking, well, if I win, I'm going to get this valuation of the strategic game. Okay, I'm doing all right. So I've got valuation of the strategic game. That's in the certainty equivalent. So I apply the utility, my preferences towards that. My probability of winning, I define here as pi as a function of the strategies of my rivals. And to calculate that, we integrate over, this is the act that I win as a function of the strategies, integrating over the probability distribution of states, conditional on the information that I have so far and the strategies that I'm imputing to my rivals. So that's my probability of winning, and multiply that by my payoff should I win. And then we invert that mapping to get back to certainty equivalent. Yeah, Bob.
So, I take it then that each of the players knows the empirical distribution.
Yeah.
What's going on? That's something the DSE.
Yep. So I'll show you that distribution soon. So this is what I think about if I'm an subjective expected utility maximizer. Now, if I'm a recursive expected utility maximizer, or if I have the smooth preferences, what I do is similar. So you see embedded in here is this expected utility calculation. So my probability of winning multiplied by my valuation of the continuation play. But then I apply this phi mapping to this. So there's some curvature here. And I integrate over the distribution of rival strategies that induces the probability distribution of winning. And then I invert both of those mappings to get back to certainty equivalence. Great. So I do something similar in the first stage. Transition, then I'm thinking about transitioning to the second stage. Same calculations, same idea. So that's a strategic game. So let me pause. Yeah, go ahead, Jeff.
Is there a unique Nash equilibrium for the strategic game?
Well, so if I condition on risk and ambiguity attitudes.
Okay, fine. Yeah.
But I have to condition on those.
That's what the ambiguity comes in, is that right?
Yeah, it's not going to be separately identified. Yeah. Great. Okay, so our data. So we have 267 episodes. We have all the information that I guess the contestants would see. So the eliminated cases, the bank offers, the decisions for both of those phases of play. The data, just a quick snapshot. These are the winnings at the end of the game, so at the end of the non-strategic game, and they're pretty skewed, particularly if you reject everything. So if you reject everything, if you look here, the median 375, the mean 10,000 odd. So it's very skewed. A little bit less so for the whole data set, and less so still for people who accept a deal. And on average, contestants are taking around a little under 20,000 Swiss francs. So the stakes are pretty good to induce preference revelation. What do the contestants do in the strategic game? First stage, about a quarter of them accept a deal. Second stage, about a third. And then in the non-strategic game, no one accepts a deal in the first 3 rounds, as the bank offers are pretty poor. And then the tension gradually builds as the offers get gradually better, and an increasing fraction of contestants are accepting offers. So this gives us our identification, certainly for the non-strategic game. Okay, so our cutoff policies. So the pictures here, so the picture on your left shows stage 1 of this strategic game. So the horizontal axis is the contestant's monetary briefcase number from 1 to 26. The vertical axis shows the fraction of contestants who accept deals. So the blue line here is the actual data. So this is actual contestant decision making. It kind of makes sense. So for low cases, most contestants accept deals. When their first case is higher, they reject. And what we want to do is we want to fit something monotonic here that's consistent with cutoff strategies. So we have a maximum likelihood routine which picks a monotonic function to fit these two things, fit both of these two charts. So you can see this orange line here is this is the cutoff strategies that we take to the data. So it matches pretty well here in the first stage. In stage 2 on the right here, I've defined here the horizontal axis now as the aggregate of the two cases. And the blue lines are the strategies or the frequency of accepting deals in the data. And the orange line is the cutoff strategies we identify. Now we estimate those two together. So when I identify a cutoff strategy, it's a pair for stage 1 and stage 2. And that matches pretty well stage 1. Not quite as well in stage 2, but it still, I think it looks all right. So these are the policies. So I guess the modal one is a cutoff of 9 in stage 1 and 29 for the aggregate. And so we've got, in some sense, more pessimistic and more optimistic cutoff strategies. Great. Now, what's the implication of those cutoff strategies for winning probabilities? And this is what will help us identify attitudes towards ambiguity. So on the left, we've got the first stage. And on the horizontal axis, again, we've got the first, the number in the first mini case or briefcase of a contestant. And so probability of winning on the vertical axis, and each line is going to depict one of those 5 cutoff strategies that we've identified for the empirical distribution. So there's one that stands out way at the top. So that's the optimistic one, when I think my competitors are just always accepting deals and never playing on, almost. So there are 26 possible cases. So this first stage saying, I think my rivals are going to exit unless their case is at least 22. And second stage, they're going to exit unless their aggregate is at least 39. So with those cutoff strategies, I think there's a high chance I'm going to win. And I become successively more pessimistic with the other cutoff strategies. Now in stage 2, We do the same thing with respect to the aggregate. And I've just given you a snapshot. Suppose my first case is 15, and on the horizontal axis, I'm showing you my second case. So my aggregate will be 15 plus whatever's on the horizontal axis. And at the start of this, we see the same pattern. So if I'm optimistic in the sense that I think my rivals will exit very frequently, then I think there's a high chance that I'm going to win. But there's something nice here, it flips around. So what's going on here? In the second round, there's a selection issue. So in the second round, if my rivals are still playing, that means that their first case must have been high. So this flips around at some point, and if I've got this really restrictive cutoff rule, it means my probability of winning is actually lower. So it's a slightly complicated, more complicated inference in stage 2. Okay, so we talk. How am I doing, Aaron? All right, great. So we talk in the paper also about the symmetric representative agent risk neutral equilibrium. I'm going to skip over that and go straight to estimates of risk and ambiguity. And yeah, all right. So I need some terminology here. So that we have an international audience. So there's an expression in Australia, people, or certainly on the East Coast, people use the word heaps to say a lot. So common usage, look at John's car, he must have heaps of money. Or this distribution has heaps fatter tails. Slightly informal. So we had to come up with a stochastic choice model. And a lot of speakers so far have been touting the benefits of the type 1 extreme value model. But really what you need to push this, it's not a t-shirt, it's beer. So I saw this last night, actually. Yeah, right. So we're going to have the heaps normal stochastic choice models. It's important to have a stochastic choice model because people are not consistent in their choices and there's heterogeneity across individuals. So we need a stochastic choice model to specify that. And we have normal distribution for our noise because we're kind of interested in quantifying that, that variation. So I define the relative attractiveness of a bank offer as the difference between the value of the bank offer and the continuation value. And we've taken logs here, so in some sense you could think of that as the ratio. And then we hit that with a few shocks. So one is a decision-specific shock, not a normal decision-specific shock. Another is we have a contestant-specific shock, and we have preference shocks as well. So to hit the preference parameters, the risk parameter, and in principle, the ambiguity parameter as well. So then we take 3 different stochastic choice models. The first, the baseline, there's no heterogeneity across contestants, but there's just the decision-specific stochastic shock. Second model, we have a random effects model. So we have consistent preferences across individuals in terms of risk and ambiguity attitudes, but there's heterogeneity in terms of this contestant-specific decision shock. And the third, we have a random coefficients model where we shut down the contestant-specific shock, but we put that instead in, we have heterogeneity in those preference parameters. Likelihood function, variation. So identification comes from variation from the strategic game, non-strategic game from bank offers, and variation the set of cases I have or monetary amounts that I could have in my case. And for the strategic game, there's variation the set of mini cases that have been revealed, which identifies the distribution of probability assessments I think that I could have that defines how much ambiguity that I have. Now we try to identify also heterogeneity parameters in some sense from heterogeneity in decision making conditional on lotteries, across contestants, and in principle also cross contestants in the strategic game. Although it turns out in practice, we're unable to identify heterogeneity in ambiguity attitudes. And I mean, we thought about this for a little while, and I think it's come down to the fact that we have cutoff strategies, binary choices, and for most contestants, the first stage cutoff is something like about 8. And they could have numbers from 1 to 26 in their first case. And most contestants have a higher mini case. And so if we have positive variance to the ambiguity preference shock, it actually reduces the explanatory power of the model. So we always hit this corner. So we can't identify heterogeneity with respect to ambiguity attitudes, which is a bit disappointing, but I think it's the way it is. Okay, so what we do is we first of all estimate just with the model just with the non-strategic game data, and then we go to the full data set. So I'm showing you here first of all some estimates based on only the non-strategic game. And did the audio just change? Yeah. Okay. Okay. And there's something kind of interesting that came out of this part that I want to highlight first. So there are a few things to come. So this table, we show you, I guess, estimates from risk attitudes. Thanks. Yep. Okay. So first of all, we have estimates of risk attitudes. So in this table, so the column 3 identify or shows you risk aversion parameters. So here we've got constant relative risk aversion and a heterogeneity or decision shock variance, indicating that there's substantial heterogeneity across decisions. And then we have the random effects model, the random coefficients model. And what these models tell you is that there's stochastic choice is important. So the random effects model shows you that the variation across decisions of an individual and across individuals are of a similar order of magnitude. So those are these two numbers here. And the random coefficients model shows you that heterogeneity or variation in risk preferences is a similar order to the mean. So that's important. So both heterogeneity across decisions, across contestants, and across decisions are both important. So stochastic choice is important. What else this table shows you is if you look at the first 2 columns, these are selected based on what happened in the strategic game. So column 2 tells you our estimates of risk attitudes for those contestants who had a high first stage case in the strategic game. So these are contestants who played on despite having a high case, which tells us basically nothing about their attitudes towards risk and ambiguity. So if I got something really high and I played on, that makes sense. The first column tells you the same information for contestants who had a lower first case. So for them, there's information content in the fact that they chose to play on. They might have had a low case and still continue to play on, indicating that if they're ambiguity and risk averse, it's not so, well, they're not too ambiguity and risk averse. And so what we see for this selection of contestants, that their risk attitudes, well, our estimate of their risk aversion parameter is much lower. So one possible interpretation is that this is consistent with the idea that there's some correlation between risk and ambiguity attitudes. Now, it's not a clean statement because our inference from the first stage embeds both risk and ambiguity. So we can't cleanly separate those, but it's consistent with the story of correlation. Same story for constant absolute risk aversion preferences. Great. All right, so let me move on. So this is for these are our estimates for the full game. and for different models. So the first two columns are subjective expected utility model. And what you notice here, there's only two columns. So we haven't estimated the random coefficients model because we're unable to identify those heterogeneity parameters in ambiguity attitudes. So we see the same kind of patterns as we saw in the previous table in terms of heterogeneity. Moving to the smooth model, which is the recursive expected utility model, we have relatively substantial estimates of ambiguity aversion. That's the alpha row here, the second row, coupled with essential risk neutrality. How much ambiguity aversion is there here? Well, the rows in the middle of this table tell you something about that. So the first row is the expected value, or is the valuation of an even bet as a fraction of the expected value of the bet. Here we've got mild risk aversion, so that's greater than 1. The second row tells you for an individual who thinks they might be facing a lottery with 10% probability of winning, or a lottery with 50%, or a lottery with 90%, and they have a 1/3 or an equal probability measure on each of those, then this is the valuation they have relative to the expected value of that bet. So they discount that substantially relative to an ambiguity ignoring bet, or an ambiguity neutral bet. So that indicates substantial ambiguity aversion. We see this also in the alpha max min model, where we see substantial weighting on the most pessimistic assessment. The max min model does not allow estimates of ambiguity. And finally, the relative entropy model, we have this really high weighting on the mode of the empirical distribution. So that suggests that people are putting a lot of weight on the mode of the strategies and the empirical distribution of strategies that are rivals. Okay, let me skip through those. So the other thing that comes out of this is the max-min model performs poorly in terms of model fit, just in pure terms of log likelihood. The rest performs similarly to the subjective expected utility model. Maybe a little bit better, but not much. So we've done a lot of work and haven't got that much improvement relative to the subjective expected utility model. Maybe the relative entropy model is doing a little bit better. Similar messages for constant absolute risk aversion. And let me stop there. Bob.
You mentioned that it seems hard to separate risk from ambiguity, and you think also said something about using the cutoff strategies, possibly helping you.
Yeah.
Some sense of what any theoretical results might be on observational equivalence?
I think there's a minefield. So if you take ambiguity out of the equation, we have a big debate about whether the expected utility model is the right one, and there are a lot of violations of expected utility, both in terms of the preference function. It might not be concave, it might be S-shaped. Violations in terms of the probability measures that we might be using, they might not be the objective ones. I think if we overlay, if we overlay the ambiguity issue onto that, I think we have the same set of issues. And one thing that we've thought about as well, there's an additional problem when you have a stochastic choice model. Functional form now matters. So most of this literature is expressing everything in terms of a utility metric. And if you have risk aversion, you're imposing concavity. And concavity is changing the objective function as well, because it's changing the treatment of outliers. And so there are lots of issues out there, and I don't think the theory is in a space to say everything is nice and clean. Yeah, so yeah.
So So does theory tell us something that can happen under ambiguity or doesn't happen under risk of view?
Yeah. So does theory tell us something that might happen under ambiguity aversion that doesn't happen under risk aversion? Yeah. So I think you know, if you look at this, then my behavior is going to vary as this distribution over probability measures changes, even if the in some sense the mean of those is held fixed. So I'm going to change as this, my behavior can change, even if I'm treating it as if aggregating over these in some sense, I have the same probability of winning or probability distribution over outcomes. So it does have content. Yeah.
Your slide with summary statistics, if I recall correctly. Yes, that one. No, yeah. So if you play it all the way, you get 10,000 on average. If you actually think about that, some deal you get 23,000. Does that suggest either that there are some contestants who are risk loving, or there are maybe many contestants who just want to be on television and they're playing the game longer? They get a per minute money metric utility out of being on TV.
Yeah, so the limelight effect, there's selection into this experiment in some sense, like there are into all of them. So I think once you're into the non-strategic game, you're on TV for the same amount of time. So there's no, if I accept a deal, unless you accept in round 3, which no one ever does, you're on the TV for the same amount of time. So I don't think it's so relevant there, but the transition between the strategic game to the non-strategic game, it is something to think about. And we do have a specification in the paper where we introduce a limelight effect, but it's not continuous in some sense. It's just this discrete choice: do I play the strategic game or not?
And then risk loving behavior.
Well, yeah, there's evidence here of risk loving, and if you look at the full model, our estimates, if we force someone to be max min, so there's extremely ambiguity averse, then the only way we can rationalize that is if they're very risk seeking. Yeah.
I don't see this distinction between ambiguity and aversion. They can have the same. When you told me that they both have the same expectation, we do something different in one and the other. We the utility function on that. And if you give me freedom on the utility function, like I thought maybe you were sitting on the utility. But
No.
if you let me, then I don't see how you can do it.
So let's have a look at the smooth model. I guess that's kind of the. Let's come all the way back. Oh. Yeah, so I've got this. Maybe it's not the best one. So I've got this utility function, and then I'm wrapping this second curvature model on top of that, and
the composition of the two is the utility function.
But what's the? I mean, to operationalize a utility function, I need a probability measure as well to do the expected utility calculation.
Yeah, I'm saying, if I said the utility function was a composition of P and mu, you're saying it's not dependent on the utility function. And I'm saying this looks to me like I could just define a new utility function and get the same answer.
Define a new utility function, a new probability measure that is going to map to this. Maybe.
I guess I was just curious whether the theorists have come up with any sort of utility function for you. I mean, we all think there is ambiguity. I don't know. There is ambiguity. I don't know if there's ambiguity or aversion.
Yeah. Yeah. How we We run out of time.
Yeah, we basically run out of time. So thanks for all the